Hello, everyone. Good afternoon. I hope you can hear me and you can see me. Excellent. Just for the interest of time, I think, are we good to get started? And I'm Maria Parisi, and this is the session about how to productize machine learning models. We're going to spend the next 40 minutes or so talking about this topic. A little bit about myself. As I said, my name is Maria Parisi. I am the Enterprise Architecture Manager for Munich Re HealthTech. I have 5 years of experience in the Munich Re HealthTech in the healthcare domain. Before that, I've worked 10 years as an architect for National Bank of Greece. I've started my career as a developer. I went to a team leader. So I have a lot of understanding about developers and their issues and the concepts of engineering. A little bit about who we are, who Munich Re HealthTech is. So Munich Re HealthTech is a division of Munich Re, which is the world's largest reinsurer group. It is a multinational organization. We have a presence in 19 countries. We are specializing in digital solutions for the healthcare insurance industry. And as a Munich Re HealthTech, we have 25 years of experience building products for the healthcare insurance market. We have our products have evolved over time. We listen to our customers. We listen to the trends of the markets, of the technology. And we also have a partnership with Oracle. A lot of our products are built and rely on Oracle technology. As you can see here, also some information about the company. We've won several awards, and we also our products have won awards from Celent, which is an organization that rates healthcare insurance products. On the map, you can see our presence, our live installations. We are a company that has global presence. We have customers from Mexico all the way to China and Singapore. You can see some of the organizations that are currently operating with our products. And I think this is a good introduction of who we are. So without further ado, I will start discussing about our topic of machine learning. So when we talk about machine learning, and this is a presentation about productizing machine learning, but what exactly is it? Why should we care about it? Why is it important? This is something that we keep hearing all the past time more and more. First of all, let's give for everyone a definition of what it is. So machine learning is actually a type of artificial intelligence which enables an application to predict an outcome without having been explicitly programmed to do so. It actually takes previous values, and based on these values, the model is trying to predict new ones. And we typically categorize the models into supervised and unsupervised. And supervised are those models which they use what we call the labels, so past human decisions. And unsupervised are models which are used just data, just fields. So machine learning is not very new as a technology, but it has become very relevant in the previous years, because right now, first of all, we have a huge amount of data that are collected from multiple data sources. We have abundant devices that are connected, and they are feeding us data, so we can do more things. We can get more information from machine learning models. And also now we have a lot of more and cheaper processing power, cheaper storage. Also, we have the prevalence of the cloud computing, which enables faster and more elastic and more scalable processing powers. And all these technological improvements have made machine learning possible for the everyday engineering world. And it started getting out of the labs, and it started becoming and coming into our everyday lives of us, of the engineering of the developers. And we need to care about it, because research and the trends of the market show that those companies that they do machine learning, they can get a significant competitive advantage versus their other companies, and they can build new products, they can develop new business models. So that is why we keep listening more and more about it, and this is why it became in our world, and we should care about it. So how do we do this machine learning thing? Typically, machine learning is something that it is being done by the data scientists, by those guys that can understand it, that they know how to train a model, and they start with this cycle. So an engagement of machine learning, a development of a model, it begins with a data set. The data scientists, which typically they develop either in Python or in R, they would get the data set, they will evaluate it, they would train a model, then score the model, see if it's good enough, and then they will probably change the features, change the hyperparameters. They do the feature engineering, hyperparameter tuning, they reevaluate, and you can see the cycle here running an experiments again and again until they come up with a satisfactory machine learning model. So the first thing we need to understand, if we as an organization, we are envisioning and building a product with machine learning, is that we need to have this capability of building the model of AI in our organization. And in order to have this end-to-end solution, so we should be able to have people that they understand the data, they can extract them, they can ingest them, clean them up most likely, and then they can do this cycle of training, scoring, and evaluating until they can have a model which produces satisfactory predictions. So, okay, I do have a model, and this is something that the data scientists do. But what we mean productize, we did our experiments, we run the cycle multiple times, but now that I finally finished with my model and I have to go outside of my Python or my R code, and I start to worry about all these operational issues of a production system. And this is the point that organizations or data scientist teams that they want to do productize machine learning model, they start to realize that there is a lot of engineering work that is required. And this is not just setting up infrastructure. It's not just setting up, my Docker or my Kubernetes, but it also involves things like building the user interface or creating a business logic of an application. So what we've realized as a company when we went on this journey is that we need to take care of these three things. So the first thing we need to take care of is how to serve our model. How do we need to build a service? So how do our model becomes available and the functionality that we build, how it becomes available to the outside world? Then we need to build some sort of application logic because the model typically cannot be able to stand alone. So we need to have a logic that interacts with it, that makes sense of the outputs of the model. And this is something that requires not just the data scientists, but it also requires a strong team of people who can understand how machine learning is binding and is relating to our everyday business problems that we are trying to solve. And here we need, programmers, and we need people that understand the ambiguity of the model, not just not just data scientists, not just pure developers. Ideally, we would like to have some kind of a blended team. And then we also need to have a team leader that could think creatively, that could understand how to utilize the model, what kind of business logic is need to build, what kind of user interface will the users make sense of it and make the value out of the model that we have created and we have built. So what are the challenges that we face? Because up to now, okay, we have our data scientist team, we have our engineering team. Well, the data scientists know how to build a model, and our engineering team, they know how to build a typical application with a user interface. So what are the challenges we need to take care of? First of thing, one of the things that we need to consider is the compatibility of the models, because the models there's not just our code. They require libraries to rely on. And then if we build and package them in one way, then if we try to redeploy a new version that probably uses another version of the libraries, we might have problems with the compatibility. Our model might not be able to run with what we have already installed with our infrastructure that we've already created. The other thing, this could be solved in a way, and one of probably a good way to solve it is to go into the cloud environment. So if we run on a cloud, then we can specify what kind of runtime we have every time we want to run a model and what kind of versions of libraries we want to use. And this sort of sorts the issue of compatibility, but it brings up the issue of portability. So if I worked on a particular cloud workspace, for example, on Google or on Azure, then will I be able to run my model only on that workspace? How can I ensure that I am able to run it and not only on a single cloud vendor, but I can move it around? So this is something that we also need to consider, not run into a vendor lock situation. Another thing that experience shows that typically becomes an issue when it comes to productizing machine learning models is the workload. Typically, the data scientists, they do not care about the workload. So they are not building the model to support the expected workload of a production application. And this is something that we realize after some time that it becomes an issue. And another thing that again relates to the kind of environment that our model would run, the target environment, is the processing power that I need. How much amount of processing power is needed and what type of processing power is needed, because it might not be available in my traditional infrastructure stack. For example, if I need a GPU, which some models do to run, that might become an issue and I need to take into consideration. So starting from the model design, what can I do when I design my model in order to make it as much appropriate for a real production deployment scenario, for a real product deployment scenario? So the first thing, and these are some things that we have gathered as a team from trying to do that, and I'm telling you that we've stumbled a lot at the beginning, and we had a lot of going back and forth until we were able to incorporate the model design into our product development lifecycle. So this is kind of our learnings, let's say. So the first thing is that the model should be flexible enough, because remember when we saw this cycle of iterations, we start building our model from a defined data set. But we have to be able to build it in such a flexible way where we can accommodate different scenarios. So if I am building with one data set and then I try to deploy it on a production scenario where I'm not having the same kind of data, I'm not having the same amount of data, I'm not having the same fields or the same codifications, that might be a problem. So I want to build my design and build my model in such a way that could accommodate different scenarios. And what we find out as a good way to do that is to define upfront a data dictionary for our model and our application. So we ensure that only data that are available from our production applications will be used for the model design, sort of a contract between the application team and the team that is building the model and designing the model. The other thing is that, and I said it again as a challenge, is that the model that we build should be able to support the performance. Typically, data scientists, in all these iterations and all these cycles, they focus on how to build the best predictions, the model that gives us the best accuracy, the best predictions. However, this might, in order to increase the accuracy, they inadvertently increase the complexity of the model. So there has to be a good and fine balance, which I will not lie to you, take some time to achieve, but we need a balance between what are the features that we need and what is the accuracy that we're getting out of the features. So this can be achieved by running experiments, and through these experiments, understanding how its feature contributes to the model accuracy. And those features that they have small or minimal impacts on the accuracy of the model, they are better to remove. Oops. They're better to be removed so that we're not increasing the complexity of the model, and such we improve the computational performance of the model. And another thing that usually gets left behind when we are talking about machine learning models, because again of the kind of experimental fashion in which the models are developed, because of these iterations and a lot of tweaking that is happening in between, modifying features, modifying hyperparameters. A lot of time, this experimenting process results in locality of code. So it might be machine learning, it might be a Python notebook, but it still is our code. It still is our asset. So good coding, good engineering, good coding guidelines should be applied also in the machine learning code. So having a version control system, following general principles like adding error handling, like adding logging, like adding documentation for our code, or running quality tools like static code analysis tools for our machine learning code. It is a good approach in order to have a good quality for the machine learning code together with the rest of the applications. And now we design the model, and we have followed all these good practices. We run our experiments, and we still need an application to run it. Our model will not run in a vacuum. It is part of an application. It is part of a larger system. And what we usually need to do is typically we have pre-processing and post-processing steps to the API that exposes the models. So either we add validations, or we translate the format of the data, add stuff like security. These are all things that typically being handled by the application where the model is consumed from. And another thing that we need to include while we design this application, because up until now, wrapping a web service, doing data transformation, doing data validation, security are kind of the things we expect to do. But an AI application should cater for two more important things. The one is the feedback loop, and the other is the model training. And let's understand a little bit what this is. The models have a characteristic where, because they rely on previous data and on previous decisions, they tend to become unstable over time. And this happens because the relationships between the target variables and the independent variables, so actually the relationship between the data that we feed the model and the output that we are trying to predict, they change over time. So the model is not changing, but the outside world does. And so that means that the predictions that we are going to get, they tend to become misaligned with the outcome that we would get if we got a human operator to do the same job. And this is an unfortunate situation which goes by the name model drift. And we have two types of drifts, which is the concept drift, but the most common one is the data drift. And this is exactly what I explained, that the outside world changes, the data changes, and the model is not a very good fit any longer. And the best way to address this drift issue is to monitor our model continuously. And how do we model it? We get through the feedback loop. So we get the actual information from the operators, from the humans, which give the response, and then we compare it with the output of our model, with the prediction of our model, and refitting the model, retraining the model with new data. And this retraining is what ensures that our machine learning models stay accurate, and they are always trained and based on the most recent data available. So what we say model retraining, it's usually the process of generating a previously modeled and regenerating a model we created previously with a new set of data, while the feature engineering, the algorithms that we've used, and even the hyperparameters, they all remain the same. So it does not involve changes in terms of the code of the machine learning, but it does change and produces a new version of the model. So this application needs to support this kind of model training, either through a training, a scheduled job, where periodically we run a retrain based on the latest data, like have a cron jobs or something like that. Or if we have an automatic model drift detection, and we will talk more a little bit in the next slides, then we can monitor the model and trigger a retraining whenever we detected a drift based on the feature distribution of the data set. So these are kind of the things that we need to consider if we want to build an AI application around the model. So what about the user interface? What kind of things are specific and are characteristic of such a user interface? And we're talking about user interface in the space where the users get some sort of value out of this model. So one of the things that we need obviously to consider is, how will my users invoke the model? How do they pass data? And how do they search and they see the results of the model output? And this could be done through user interface, but most typically could also be exposed as a kind of integration service. So I can see information through my application, but I also enable the integration of my model with some sort of exposed API. We should also be able to provide to our users dashboards, so they can see not only the model outputs, statistics of the data, but also they are able to see the model performance, all the metrics, how the accuracy, confusion matrix, all this information that gives them the confidence that the data that are getting as an output from our model is good enough. Also, very important, we've mentioned also in the previous slide, give an interface so the user can provide the actual results, the actual values, and also close the feedback loop, which, as we mentioned, is very, very important to monitor the performance of our model, detect any drifts, and use also the data collected through the feedback loop to be able to retrain the model and have always a relevant model version. And another thing that we can consider offer through the user interface, it is selecting the model version. As we will see in the next slide, how maintaining the model, I might want to be able to select on my application, on my user interface, which version of the model I want to run, or select a version of the model to run in a kind of a shadow mode, where I collect information, I run predictions, but they are not impacting my application results, in order to be able to monitor a new version of the model and compare it with the previous one. So these are all things that are good candidates to provide through the user interface. So now I've built my model, I've designed my application, it has its user interface. What other things do I need to know as an engineer? What other things are distinct to this kind of work of integrating machine learning models into applications? And another thing that we need to cater here is the quality. And starting from the bottom up, this pyramid of testing and quality, we can see that apart from testing my application, my services, my UI, my business logic, I also need to consider running quality checks and running validations on the data sets that I'm using. Because machine learning model training is so much dependent on the quality of data that I use, if I'm not doing any quality of assurance of this data, I will probably not be able to produce any valid models. So one of the things that I need to, when I'm talking about a productizing model, when I'm talking about running models that produce useful business insight, useful business information, I need to be able to ensure that my data are correct. So here we have a kind of cycle for quality on the data. The other obviously is how to test the machine learning pipeline, all the data transformations, the validity of all the machine learning code that I'm writing. On the middle layer, I have the model performance and the model bias, which is understanding the quality of the model that I have produced. And this is typically what happens after the iterations that I've run, but also testing and assuring the quality of the model throughout all its production life cycle. So the difference with let's say a deterministic application, the difference with a software system that I've built, I've tested, and I keep running is that unless the business scenario changes, this will always keep performing in the same manner. When I have a validation, my validation will always provide a valid output how many times I run it. But with the models, there is this ambiguity and uncertainty that relates to the data. So I have to be able to monitor the quality of my model throughout, even after it is on production and live. And of course, I need to be able to run my typically integration and end-to-end tests. And what I need to be careful here when I say end-to-end tests, before I run something into production and I have my business operations relying on machine learning model outputs, I have to be able to demonstrate through analysis of statistics the value of the output of this model. A little bit about the continuous delivery of the machine learning. And here you can see that it's a little bit different. The paradigm relates to the typical application, because in my typical application, what I do have is that I have my code. And my code is in my repository, and I have some automation that I take my code, I build, and I deploy to the production. Here, the artifacts are not just code. Here, what I need to consider, what I need to version, protect, maintain is my data. The training code, which I use for the model building, and these are my assets, and I need to version them and protect them, which they generate a model, which is again, let's say a meta artifact. And the code of the model with my application code is eventually what gets deployed into the production. So if I'm talking about ensuring continuous delivery for a machine learning application, I have to consider about data, model, and code. And when we're talking about deploying it, where do I deploy? I mentioned as part of the challenges and as part of one of the factors that make it more relevant, make models more relevant today, as that we have cloud. And indeed, deploying on end-to-end cloud solutions is a very good option for many machine learning applications. And in this slide, you can see a summary of pros and cons when we're talking about on-premises versus cloud installations. When we're talking about having everything locally on our data center, we don't need to pay a recurring subscription cost. On the other hand, it requires an initial investment. On the cloud, however, when we are running a heavy or an intense model and we have to use costly processing power, it might become more costly in the long run versus having it on our own machines on our own processing power. The scalability, however, that might be required, obviously in the cloud, everything is more elastic, it's more scalable, while when we're talking about local on-premises deployments, we need to do more advanced planning and we need to use our administrators for the system to scale. Security is something that might be an issue because we need the data on the cloud. If we're talking about cloud, we need to have the data there. So we need to have our production data. Maybe we need to have sensitive data. And we need to have them on the cloud in order for this thing to work, because data sets are needed. And we might end up with a situation, not that the cloud providers are obviously secure, right? But there might be local regulations that impact the ability to store sensitive or private data on a cloud provider. So this is something that might drive us our decision to have it on locally. And data gravity. Data gravity is is a concept that our data need to be close to our application. So where the data are generated, not have, we wouldn't want to run into a scenario where our data are in a local data center and we run on the cloud and vice versa. So if we have all our applications that generate and use the data in our local data center, having just this machine learning bit running on the cloud might not be the best idea. So we've already talked about hardware. If we need to have it locally, we need to configure it. We need to be able to plan it, do capacity planning, plan ahead. While it's on the cloud, things are a lot more simpler. And the setup of the libraries, or having a Docker image with all the Python libraries that I need to run it, might require some extra effort. While on the cloud, it's literally just a click of a button. So in general, if we want to do a summary, what would be a good idea? Cloud usually is a good idea when we are starting up. So it reduces the engineering and the configuration overhead that is required for our data scientists team to get started. While on the long run, if we are investing heavily in running a lot of applications, we might consider cost-wise to bring something on local data center. And finally, the machine learning maintenance process. As we have all our tests, we've done our designs, we've done our best effort, we've built our applications, we've tested, we've deployed, we have a continuous cycle. And how do I maintain this model? And this sort of slide ties up together what we've said so far. So we have the model monitoring that we've mentioned. And this is something that should be done periodically, either automatically or by a specific role by data scientists. And for the model monitoring, we need to capture and compare results with the feedback loop, with the actual human decisions, if we're talking about supervised models. We need to have and determine some quality gate that we review periodically about when our model needs some maintenance, when our model no longer performs as it should, and get some kind of alert where the quality gates are no longer met. If the quality gates are no longer met, ideally our data scientist team should do some sort of investigation. We can try to retrain the model, but it seems that we're not getting the quality that we are looking for. So this investigation sort of requires the production data, requires some, again, experimenting in order to understand what changes do I need and come up with a new model version. Again, we need to test it. We need to have specific criteria of when our model is good enough to replace the model that we have in production. And I'm talking not just retraining here, right? I'm talking about changing features, changing algorithms, maybe. So, and also the criteria for when a model, the success criteria for when a model is ready to go to the production, is something that we should be reviewing periodically. And after I'm ready, here comes what I've mentioned earlier about shadow mode. I have a production, imagine that I have a production system that is using a model and is getting an output which is used for some business reason. It's making doing some decision making based on that output. If I just deploy a new version of the model without previously knowing how this will impact my decisions, I might end up with unforeseen situations on my business operations. So usually what we suggest doing is to run the model in what we call a shadow mode. So we feed it the same kind of data which we feed the live model, and then we store the decisions, and in parallel, we monitor the performance of the model until we are confident enough that this performs better than the previous version. And here where the actual go live criteria come in. So what kind of quality gates should be met, not just to deploy on my production environment, but to replace the previous version, to replace the previous pipeline, and to adopt this new model version for my application from now on. And this is where the go live comes in. And through this cycle, I have my application, I have my model, I'm able to monitor the performance, and I'm able to maintain it in order to keep it relevant with the change in data from the outside world, in order to be able to get the actual business value that I am anticipating out of these machine learning model-driven applications. And I'm hoping you enjoyed this presentation. If you have any questions, there is a Q&A button. You can write it in this Q&A chat, and I'll be happy to answer. If there are, I'll wait a little bit more. If you have questions, you can see my email is here. You can see the information of the company. You can reach us as well. Alternatively, if you want to speak, you can raise your hand and you can speak your question. Okay, we have a question. How do we handle outliers? And I mean, are you referring to outliers of clustering, for example? Because if we are referring to the, we do have a clustering model. We actually have two kinds of outliers, are either observations that have not been able to be attached to any of the clusters. And we have a threshold. For those that produce an outlier score above the threshold, again, we handle them as outliers. And usually what we do is we have a monitor, a business dashboard, where the users can go in and check whether this makes sense and give it some sort of understanding from a business perspective. So we treat them as kind of a business scenario that needs to be reviewed by the actual human operators. Any other questions? You can raise your hand, you can type your questions. Okay, so thank you everyone for taking your time to listen to this presentation. And I wish you all good evening and to enjoy the rest of the code week.